Hello, hello, hello. In this episode of What's the Big Idea, we're going to be talking about drag forces. And drag forces have lots of practical applications. Locally, you'll be launching ping pong balls and trying to land them in a solo cup in your lab activities. And to be successful, you're going to have to understand a lot about drag forces. If you play ping pong, you're very aware of drag forces. If you watch a baseball game and wonder whether that batted ball is going to be a home run or a routine fly, drag forces are really important for that. And if you're concerned about how much energy you consume when your car cruises down the highway, drag forces are really important for that very important problem. But there are also some bigger ideas about drag forces that I want to get to, how the laws that govern drag forces are really quite different in an important way from what I would call fundamental laws of physics, such as the law of gravity. So let's dig in. So let's consider the case of a ping pong ball traveling, say, from left to right at some velocity, which we'll call v ball, and it's moving through still air. And now I want you to imagine what the situation looks like from the reference frame of the ping pong ball. If you were riding on board the ping pong ball, relative to you, you would see the air moving to the left at a speed that's the same as the speed of the ball moving relative to the still air. So we can write that this vector v air here is just same magnitude but opposite direction to the velocity of the ball when viewed from the reference frame of the still air. So we should start off by saying what we mean by a drag force formally. I'm going to define the drag force as simply the force that's exerted on the ball as a result of its motion through the air. So it turns out it's much easier to think about this problem viewing it in the frame of the ball. If we have air blowing from right to left and hitting the ball, can we calculate the force that the air exerts on the ball? Well, to do that, we need to come up with a model. This is not going to be an exactly true statement, but a model is something that approximates reality. So the first observation which we'll make, and this is not a model, it's really a fundamental truth, is that the third law, Newton's third law, tells us that if we want to calculate the force that the air exerts on the ball, it suffices to calculate the force that the ball exerts on the air, because then by virtue of the third law, you just put a minus sign in front of that force and you get the force that the air exerts on the ball. So now here comes the model part. We have this air that's blowing from right to left, and it's going to hit the ball, and we have to make some assumption as to what happens to the air after it hits the ball. And a reasonable assumption, it's not exactly true, but it's not a bad approximation to assume that what happens is that the air reflects off the ball. It bounces off. It just reverses uh, direction, but keeps going with the same speed. So we'll colloquially refer to this air after it's interacted with the ball as the reflected air. And with that assumption, the change in the velocity of the air due to its interaction with the ball, delta v sub air, is clearly going to be equal to, it's going to point in the direction opposite to the initial direction of the air, and its magnitude is going to be twice. So delta v air is just minus twice the initial velocity of the air. Now, we can use Newton's second law to state that it's got to be true that the force uh, that the ball exerts on the air, just by virtue of the second law, is the amount of mass of air that bounces off the ball times delta V air over delta T, where M refers to the amount of mass that bounces off the ball during a time interval delta T. So this is just by consequence of the second law. Well, how much mass bounces off the ball during a time interval delta T? Well, it's going to be all of the mass that's contained in a cylinder of cross-sectional area A, where A is the cross-sectional area of the ping pong ball, and the length of the cylinder is just the distance traveled by the air during the time interval delta T, which is just the speed of the air times delta T. So we can write the force that the ball exerts on the air. If I want to calculate the mass, I can just write the mass as the density of air, the amount of mass per unit volume, times the volume of the cylinder that we just referred to, which is the speed of air times delta T, times delta V air over delta T. Don't despair, we're almost there. These delta T's cancel, and what we're left with, if I plug in for delta V air here, is that this force is equal to rho A V air times minus 2 V sub air. It's a vector. Or this is equal to, I pull out the minus sign here, there's a factor of 2 rho A, and then here's an important point, it's proportional to the speed of the air squared, and then the direction, this is a unit vector that points in the direction of the air, which is pointing to the left, and this minus sign makes the force point to the right, which is what we expect. The force that the ball exerts on the air is going to point to the right. And now remember, we were ultimately interested not in the force that the ball exerts on the air, but the force that the air exerts on the ball. And from the third law, that's just minus this. So at the end of the day, what do we have? We have that the force that the air exerts on the ball, which we'll call the drag force in this case, is equal to minus 2 times the density of the air times the cross-sectional area of the ball times the speed of the air squared, with, whoops, there's a plus sign here, and not a minus sign, times V hat air, right? Because there are two minus signs. This minus sign and this minus sign leads to a plus sign. Okay, so that was a sophisticated argument. You should go through and play this back carefully and make sure you understand the steps. But at the end of the day, this is the result that we want to focus on. So a couple of comments. One is, again, the drag force points in the direction, the same direction as this vector here, and that makes sense. That the air is blowing on the ball so that the force is to the left. More importantly, this factor of 2 here, we're not going to take too seriously because we made a sort of a rather crude approximation here to assume that the air is just perfectly reflected off. That's not necessarily true. So we're going to take this with a grain of salt. But the stuff that's really important are these factors here. We are predicting that the drag force should be proportional to these 3 factors. It should be linearly proportional to the density of the air. It should be proportional to the cross-sectional area of the ball. And importantly, the drag force should be proportional to the speed of the air squared. And again, now if we view this from the frame of the still air, then the speeds that we're talking about are not this. It's the speed of the ball relative to the air. So really, we can sort of ignore these subscripts here, and it's really V just stands for the speed of the ball relative to the air. So this argument, the important conclusion is that we expect the drag force to grow pretty dramatically as the speed increases. It's proportional to the speed squared. And anybody who's ridden a bicycle probably notices this. You really, as you speed up, you really begin to notice rather dramatically the effective drag as you start going faster. Because if you double your speed, you quadruple the drag force. So this really sets an upper limit on how fast cyclists can go. And it also explains why, if you're cycling, you sort of hunch over and try to minimize your cross-sectional area to try to minimize the drag forces. And it's also very important if you're designing a car and you want to get good mileage on the highway where you're going fast. It's very important to streamline the car so that the effective cross-sectional area of the car is as small as possible, because that's going to reduce the drag forces. And then the last thing I'll say is that because the drag force is proportional to the speed squared, it actually makes it hard to find analytical solutions to problems. So if you try to calculate the motion for a projectile where there's no drag force, it's quite easy, and we've done that. But if you try to calculate and try to find an analytic solution when you take into account drag, it actually is quite difficult, and it really pushes you towards doing numerical solutions. Because as you'll see, when you do these VPython simulations, it's pretty easy to modify the calculation that you've done without drag and just change the force by adding a term that looks like this. It's just literally a few character strokes change in the program, and you can add the effective drag. And you can see in this screenshot here, you can definitely tell that drag is present, because if you had projectile motion without drag, the horizontal component of the velocity would not change, because the gravitational force is only in the vertical direction. But here we can see that there's definitely drag, because if you look at the horizontal distance between the successive dots, it's getting smaller, and it's particularly noticeable at the beginning of the motion, because that's when the ball is moving the fastest, and that's when the drag forces are the greatest. So anyway, you'll have ample opportunity to explore the effects of drag both experimentally by launching ping pong balls and by doing simulations in VPython. And we'll finish up by watching this little video, which you'll have a chance to analyze in detail, frame by frame. But here we're going to drop a ping pong ball. This is my wife, Nancy. And this is a ping pong ball, and this is a baseball. And this is Miles, my dog. And let's watch what happens. Nancy's going to drop the ping pong ball and the baseball at the same time. And which do you think is going to hit the floor first? Let's watch. There we go. And the baseball is ahead and gaining. And then the ping pong ball. And then a little while later, Miles reacts. So drag clearly had a bigger effect on the ping pong ball than it did on the baseball. And that's it for this episode of What's the Big Idea? Hope to see you again soon. Bye bye.